Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll compile our Fortran program for matrix multiplication and conduct performance testing. However, I want to emphasize a cautionary note. It's best to avoid creating your own matrix multiplication routine. Expert-developed libraries offer significantly better performance than what you could achieve independently. We're using matrix multiplication as an example to explore parallel computing concepts. Remember to apply what you learn to your own unique problems, especially when libraries for those problems don't exist. In my previous video, I mentioned that we would discuss compiler options in the Python script. These options include O3 and O-fast optimizations, as well as specifying the CPU architecture using the march option. Specifically, we've specified the CPU as a Sky-lake AVX-512 architecture. Before diving into compiler options, I've updated the Python script. The addition is the calculation of floating point operations, or flops, for matrices of size n squared. The flops for matrix multiplication are computed as 2 multiplied by n cubed. This considers the nested loops in the Fortran program, with each iteration involving one addition and one multiplication operation. The loops iterate over ij and k, resulting in n cubed. To simplify the calculation, I've divided n by 1000, resulting in the calculation of gigaflops. At the end of the Python script, we've added a printout of the performance measure in gigaflops per second following the calculation of the mean wall time. To access the manual for the iFort compiler, simply type man iFort at your command prompt. The manual will be displayed in your terminal. However, it's worth noting that this manual is extensive and may be impractical to navigate. The O3 option is first mentioned in line 10,830 of the manual. It may be more efficient to seek information about the compiler through alternative methods. Another approach is to use the iFort command with the help option. This will display information in your terminal. Alternatively, you can redirect the output to create a file named ifort_help. You can open the help file using the Emacs editor. This allows you to review the information and make notes on any key insights or experiences you've gained. As you scroll through the help file, you'll notice numerous O options available for optimizing your Fortran program. While we've opted to test O3 and O-fast, you have the flexibility to experiment with other options as well. As you continue scrolling through the help file, you'll come across the march option, which allows you to specify the architecture of your CPU to the compiler. It's important to note that this option can only be utilized if you're familiar with the architecture of your CPU. We can search online for information about the Intel Xeon Gold 6138, used in the normal compute nodes on the Saga Linux cluster. According to Intel's website, this CPU belongs to the Sky-lake architecture. As we continue scrolling down the page, we notice that the Intel Xeon Gold 6138 features the Intel AVX-512 instruction set extension. Before utilizing the iFort compiler, we need to ensure access to the latest version of the Intel Fortran compiler. We achieve this by employing the module command. Initially, we clear our environment using module purge. Then we load the latest Intel version using module load Intel/2023A. To see which modules are loaded with the latest Intel version, we can use the command module list. To explore detailed tutorials on module load and accessing software on Saga, you can find comprehensive information in the HPC onboarding videos available on this YouTube channel. The onboarding videos provide in-depth explanations and practical examples across various topics. Before we proceed with compiling and performance testing, let's first remind ourselves that the dimension of the matrices are equal to 2048. Before proceeding, we need to switch from the login node to a normal compute node using our Python script for interactive job setup. It's important to mention that we're now specifying total memory usage with the MEM option. We'll cover this topic in more detail later and discuss how to monitor memory usage. Now, let's recall the structure of the loops in our Fortran program. The triple-nested loop is where the majority of the computation takes place. Executing the Python script testing on the compute node involves compiling with the iFort compiler, executing the executable 3 times to measure wall time, then calculating the mean wall time and performance measurement in gigaflops per second. Notably, the wall times range from 24 to 29 seconds, and the march option doesn't seem to have a significant effect. This discrepancy seems unusual, suggesting a potential issue. Additionally, the observed performance measurement is notably low, less than 1 gigaflops per second. Since something isn't working as expected, let's attempt an alternative method for performing the accumulative summation. We'll try using the intrinsic function sum. While it appears that the loop is now only double-nested, there is an additional loop due to the array notation inside the intrinsic function sum. We'll implement this method in the Fortran program mxm sum. Before executing our testing Python script, remember to update the name of the Fortran program. Executing the Python script once again on the compute node reveals that the wall time ranges from 23 to 31 seconds, with no noticeable effect from the march option. Unfortunately, our new method for performing the accumulative summation did not resolve the issue, and the performance measurement in gigaflops per second remains below 1. Let's explore another approach for the accumulative sum. Upon considering the problem, we recognize that matrix C can serve as the accumulative variable instead of TMP. However, this requires initializing all elements in matrix C to 0. We'll implement this approach in the Fortran program mxm. Remember to update the name of the Fortran program before executing our testing Python script. Executing the Python script again on the compute node shows a significant improvement in performance. The execution time has dropped to just 1 to 2 seconds, particularly noticeable when using the march option. It appears that our latest approach to performing the cumulative summation has effectively addressed our problem. When measuring performance in gigaflops per second with the march option, we achieve about 12.5, which is approximately 20 times faster than our previous methods of cumulative summation. The wall times of 1 to 2 seconds are short. Let's confirm the performance measurement by increasing the matrix dimension. We'll set n to 4096 and reevaluate. It's crucial that we extend this adjustment to our Python script testing. Otherwise, our performance calculations may yield incorrect results. Executing the Python script on the compute node again yielded a wall time ranging from 11 to 22 seconds. The impact of using the march option is evident. With this option enabled, we achieve approximately 12 gigaflops per second. whereas without it, the performance is around 6 gigaflops per second. Fortran provides an intrinsic function for matrix multiplication called matmul. Let's experiment with this function to evaluate its performance. Once again, remember to update the name of the Fortran program. Upon re-executing our testing Python script on the compute node, we observe that the performance achieved with the intrinsic function matches that of our previous method for accumulative summation. How can we determine the memory usage of our Fortran program? The job number for our last interactive job with the intrinsic function matmul was 10, 44, 19, 59. Using the Linux command job stats with the J option, followed by the job number for our last test with the intrinsic function, employing n equal to 4096, reveals that the memory usage was approximately 388 megabytes. We can also utilize the Linux command cef followed by the job number. This command reveals that the memory usage was approximately 388 megabytes, indicating that we only utilized about 40% of the requested memory, as we initially requested 1 gigabyte. In summary, the recent cumulative summation method proved more efficient than our initial TMP variable approach. In the upcoming video, we'll analyze compilation reports using the QOPT report option for the iFort compiler, as outlined in the help file. Additionally, we'll explore vectorization and single instruction, multiple data for single CPU core parallel computing. As mentioned at the beginning of this video, it's advisable not to write your own code for matrix multiplication. There are efficient libraries available for this task, such as the math kernel library. However, integrating and compiling it can be complex. Another option is to use Python libraries like NumPy, short for numerical Python. You can write most of your code in Python, but when you need high computational power, NumPy libraries can help. If you find certain functions missing in NumPy, you can write them in Fortran and easily use them in your Python code. We'll cover how to do this in our upcoming videos. In our next video, we'll start by examining the compilation reports to understand the issue with using the TMP variable. We'll also discuss parallel computing on a single CPU core. I am looking forward to the next video. Wishing you all happy computing in the meantime.